Let's continue our discussion of Markov chains by thinking about their steady state behavior. And what I mean by this is just if we start out a Markov chain in one state and we let it run for a long time, then we expect that the actual state will be some random variable. So you might occupy each state with some probability, and we want to see do those probabilities settle down into something in the steady state. Okay, so recall that we've been interested in homogeneous, meaning that the transition probabilities are always the same, finite state, and discrete time Markov chains. Okay, so there's a sequence of random variables, and they live on range 1 to k. And so here's an illustration of those values in the range, and they're fully specified by their initial distribution, so the probability of occupying a state at time 0, and the transition probabilities that we were writing as p, j, k. And those are defined for j, k going from 1 to capital K. And these transition probabilities are the probabilities of going to state k starting from state j, and the homogeneous assumption means that these are always the same regardless of time. So from time 0 to time 1, and from time 57 to time 58, and so on, all of those conditional probabilities are given by the transition probabilities. Okay, so we usually draw these on the Markov chain. Here I'm going to illustrate all of them, right? So I have all of these possible transition probabilities going from node 1 to node 2 to node k and back, right? And I write the values on these arcs. And in this particular illustration, what we've done is we've assumed that all of these transition probabilities are positive. If one of them was actually equal to 0, we wouldn't draw an arc between the corresponding nodes. Okay, we also define the state probability vector at time t to be a vector that contains the marginal PMF of xt, so the occupancy probabilities of each state at time t. And that, we decided, evolved according to this update equation. Pt plus 1 is the transition matrix transpose times pt. Okay, so this transition matrix is just p11 up to p1k, all the way up to pk1 and pkk. And this holds all of the transition probabilities in a matrix and makes the computations a lot easier. The row index j is the current state, and the column index k is the next state. Okay, and what we want to know then is, how does pt behave in the long run? So does it settle down into some kind of limit? So can I take a limit as t goes to infinity and get a reasonable value, or does it bounce around or oscillate forever? And it turns out the answer actually depends on the structure of the Markov chain. What do I mean by structure? Well, we're going to see as we go along, but basically what it means is it depends on what arcs do I have for non-zero probabilities and not on their values. So it just depends on which probabilities are positive and which ones are 0. And it's something we can do by inspection, by looking at the structure of a Markov chain. All right, well, let's start out with an example to motivate our study. So remember, in a previous video, we were looking at the following Markov chain. Okay, it had 2 states, and it had these transition probabilities. So the transition probability matrix was the 5th, 4/5, 3/5, and 2/5. And we previously showed that if the initial state probability distribution is 1, 0, meaning that we start in state 1, then P1 and P2 are given by the following 2 equations. So I use the update equation. I multiply 1, 0 times the transpose of P, and then I got a 5th and 4/5. And then I could take that 5th and 4/5 and update it again to get P2, and I would get 13 over 25 and 12 over 25. And what I'm going to do here, just as an example, is I'm going to continue to use this update equation, Pt plus 1 is equal to transition matrix transpose times Pt. I'm going to plot these 2 probabilities, the occupancy probability of state 1 and state 2 at time t. I'm going to plot that from 1 to 15. Okay, so I'm computing this on my own, and I'm just going to visualize these values for you. So we started out at probability 1 in state 1. So you can see that plot starts at 1, and probability 0 for state 2. And then we bounced to be a 5th and 4/5. Okay, then we bounced again to be 13/25 and 12/25. And that's going to keep bouncing around. So let's just follow it for a bit. So it keeps bouncing, and it seems like they're getting closer and closer to some asymptotic values. And it's hard for me to illustrate that at this precision, but it turns out if you take the limit, it goes to 4/7 for the higher one, which is pxt2 in the limit, and it goes to 3/7 for pxt1 in the limit. And these are the asymptotic values. Okay, so in the long run, what this means is that state 1 is occupied 3/7 of the time, and state 2 is occupied 4/7 of the time. And it doesn't actually matter how you choose the initial probability state vector, you will always settle down into these values. So do all Markov chains display this kind of behavior? Okay, so this was nice, it settled into something. Is that always true? And for those that do, how do we actually calculate these limiting values? So I didn't show you how to do that. We just made a plot, right? And we're just inferring now that these asymptotic values are there, but we're going to learn in this video how to be sure that they're there and how to calculate them. Okay, formally, I'm interested in determining the limit, right? So I want to know the limiting probability state vector. Okay, we're going to denote this by this variable pi vector, which is the limit of pt vector as t goes to infinity. And so it has components pi 1 up to pi k, where pi j is the limit of the marginal of xt as t goes to infinity evaluated at state j. So it's the probability that at a given time you're sitting in state j. I take the limit of that probability. So I try to see in the long run, does that probability settle down into some asymptotic value? And I just try to figure out what those probabilities are for each state. Okay, so by normalization, these are probabilities and they need to sum up to 1. But before I get into taking any kind of limit, I want to be sure that the limit actually exists and I'm not just bouncing around between some values. So the problematic cases can be examined as following. So there's this first case where there might be periodic oscillations and the Markov chain may bounce around forever and never converge. Okay, as an example, consider this two-state Markov chain. Okay, and so you always switch states. So the transition matrix is 0, 1, 1, 0. And notice that if we presume that you start in state 1, then you will spend all of your even times in state 1 and all of your odd times in state 2. And then you will get the following sequence of transition probability, state probability vectors. So you'll see first 1, 0, then you'll see 0, 1, then you'll see 1, 0, and you'll see 0, 1 again, and so on. This will just keep repeating, and there will not be a limit. And you might think the issue is the initial distribution, but that's also not true. You could try some other initial distributions, and you will not settle down into a limit. Okay, so if you take the initial distribution as alpha and 1 minus alpha, you'll have the same problem where you'll keep bouncing around to 1 minus alpha and then alpha, then you'll go to alpha and 1 minus alpha and so on. It'll keep repeating. Okay, and so there will not be a limit. And at this point, it's worth pointing out that you might look at this alpha and think, oh, if I pick alpha equals to 1/2, then it'll stay the same. It'll always be 1/2, 1/2. And that's true. But what we want from this limit is that no matter where you start initially, you settle down into the same limit. And that's not true here. The second problematic case is that you might find that some states are not reachable or unreachable from other states. Okay, let's look at an example to see what this means. So let's say I have 3 states, 1, 2, 3. And I can loop on 1, I can only leave 2 to go to 1 or 3, and I can loop on 3. And let's say that initially I'm going to start on 2. Okay, that means that my probability vector is initially 0, 1, 0. And so with probability 1/2, what am I going to do? Well, I'm going to jump from initial state x0 equals 2 to x1 equals 1. Okay? So in this case, what's going to happen is now the probability state vector is going to be 1, 0, 0 for all time. I'm going to stay on 1 once I've jumped there. But it's also possible. So the remaining half of the probability goes to jumping from this initial state x0 equals 2 to x1 equals 3. And then once I'm settled onto 3, I just loop forever, and my state probability vector is going to be 0, 0, 1 for all time. Okay? And so what this means is there's not going to be a unique limiting probability state vector. So there's no unique pi. What's troubling about this is that the whole thing turns on a very tiny choice that gets made at some point in the sequence. So in this case, the fact that I jump from 2 to 1 or 2 to 3 just once completely changes how this limit looks. And that's not what we want. Again, the behavior that we want is no matter where you start out, you always settle down into the same limit. And if you have these kinds of unreachable states, that will not happen, right? So what your limit looks like will depend very strongly on some very small events. And so to avoid these kinds of problematic cases, we need a way of looking at Markov chains and systematically classifying them so that we know that this can't happen. So this is actually going to take quite a bit of work in terms of definitions. Once you get used to it, it's not going to be such a hard thing to do, but there are actually going to be quite a few definitions that follow. We're going to define each term, work through an example, and just keep moving on. And hopefully by the end, it's pretty straightforward and clear. You might need to work out a couple more problems to get the hang of it. So state K we'll call accessible from state J, and we'll show this with an arrow going from J to K, if it is possible to reach state K starting from state J. So if I put you in state J, can you make it to state K at all? And it doesn't matter how many time steps you take. You could take more than one, right? So I'm just asking that the transition probability for n steps is positive for some value. Okay, we're defining this pjk at 0 now for our own convenience, okay? And basically, this is just the probability of staying where you are in 0 time steps, meaning that if you look at pjk 0, it's 1 if j is equal to k and 0 if j is not equal to k. Okay, the reason I want to do this is so that I always have j is accessible from j. It's always, you're always able to access your own state if you start there. So you might want to go back and define this accessibility for time steps 1 onward, which is fine, but then later you'll have to come and make an exception and say each state is accessible from itself. You can do it either way. We're going to do it this way by allowing this 0 time step. The example is going to be the following. I'm going to draw this Markov chain and all of these arcs, but unlike before, I'm not going to label the arcs. And the reason is, for state classification, it doesn't matter, all right? So the actual pjk values do not affect this process of classifying states. The only thing that actually matters is whether or not they're positive, okay? And that is indicated by the presence or absence of an arc. So presence of an arc means there's a positive probability. And if you notice, this accessibility definition just says the probability needs to be positive for some n, right? So I don't actually need to know what the value is. So let's just write down which states are accessible from each other. Okay, so I'm going to write all of these different cases. So the ones that I'm going to get for free are these states to themselves. So 1 to 1, 2 to 2, and 3 to 3. That's all by default, okay? And then I'm also going to look and see that I can go from 1 to 2. So I have 1 to 2. I can go from 2 to 1, so I have 2 to 1. And I can go from 3 to 2. And I can go from 3 to 1. In that case, it was 2 time steps. But it is not possible to reach 3 starting from either 1 or 2. Okay, so I don't write those relations. All right, the next thing I'm going to define is states j and k communicate, and I write this with a 2-directional arrow, if j can go to k and k to go to j. So basically, if j is accessible to k and k is accessible to j, then they communicate. And we have, by default, that J communicates with itself, since we have that J is accessible to itself. Intuitively, what this means is that it is possible, right? So the probability is greater than 0 to go back and forth between states J and K, maybe with many steps in between, all right? It's okay to take many steps, but I can do it. A communicating class C is a subset of states, so a subset of 1 to K in our case, such that the states that belong to the class C communicate with each other, meaning that if J is in C, then K is in C if and only if J and K communicate. This is easier to see through an example. The main thing I want to point out about this is that a finite state Markov chain can always be partitioned into disjoint communicating classes. Okay, so this is a way of partitioning states. So here I'm going to draw this example. I'm going to draw 6 states and all of my arcs. Okay, so I'm just drawing some example to have some different communicating classes, right? And let's get to work here. So the communicating classes, remember, are the states that can go back and forth between each other. So what is C1, the first communicating class? I can go from 1 to 2, 2 to 3, and 3 to 1, and so on. So this is a class. I can't go from any of those states to 4 or to 5 or to 6. There's no arrow, so they're not in the class. So I have 1, 2, and 3. The next class is just going to be 4. And the reason is you can leave 4 to go to other states, but you can't come back. So no other states communicate with 4. 4 only communicates with itself. So I have 4. And then the last class is just 5 and 6. They communicate with each other. You can go back and forth between 5 and 6, but you can't come back from anywhere else. Okay, so this is something that might seem a little bit technical, but looking at this drawing, all you need to do is figure out which states can go back and forth with each other based on the existing arrows, and those get drawn into a single class, and then you can group the states in this way. We're going to see why that's useful. Okay, so the first thing that we're going to use this communicating class for is to say that a Markov chain is irreducible if it only has one communicating class. Okay, we'll just see that again through some examples. So in this case, I'm going to have 4 states. I'm going to draw the following arcs from 1 to 2 and back, from 3 to 2, 3 to 4, 4 to itself. So we're going to have the following communicating classes. So we need to see which states can go back and forth with each other. I'm going to see I can go back and forth between 1 and 2, so that's going to be a class. 3 can't really do anything, so it's just on its own. And 4 is also on its own. It can't go anywhere and come back. So I have 3 classes. Therefore, this Markov chain is not irreducible. All right, let's draw another 4-state Markov chain that is. Okay, I have 1, 2, 3, and 4. And I have the following arc structure. All right, so I have these, and then I have from 1 all the way to 4. And what's interesting about this is that 4 is not directly reachable from 2 or 3, but we're going to see that that doesn't matter. Okay, so let's look at the communicating classes. So I'm just going to illustrate that I can go from 1 to 2 to 3, then I can go back to 2, back to 1, back to 4, and then all the way. So this allows all of them to eventually connect with each other. So all of them are in the same communicating class. And I say that the Markov chain is irreducible because there's only one class. We say the state J is transient if there is a state K somewhere in the Markov chain that you can access from J, but there's no way to access J starting from state K. Intuitively, what this means is that once you reach K, starting from J, there's no way back. You can never return, okay? So there's a path from J to K, but there's no path back from K to J. So any probability that leaks from J to K is never coming back, all right? And this is called transient because eventually you will not find yourself in state J. You will find yourself in state K or some other states, but eventually you'll leak away all the probability of J. If state J is not transient, meaning that there's no state K for which this happens, we will call it recurrent, and that refers to the fact that you can always recur back onto state J. And it turns out that all of the states in a communicating class are coupled together in the sense that they're either all going to be transient, meaning that if you find a single transient state in that communicating class, then all of them will be transient because they'll all leak away probability, or they will all be recurrent. And if they're all recurrent, that means you have to check that none of them are transient. And in the Markov chain, you will always find at least one class that is recurrent. Let's do an example. Okay, so we're going to have 5 states in this example. Okay, so we have these arcs going from 1 to itself, 2 to 1, 2 to 3, 3 to 2, 3 to 4, 4 to itself, 4 to 5, 5 to 4, and 5 to itself. So they're going to be communicating classes. Let's start out on the left and see. So 1 can only stay on itself, and then we're going to have another one which is just 2 and 3, and the final one is going to be 4 and 5. Okay, and so looking at this picture, we can see that classes 1 and 3 are recurrent, meaning that they don't leak probability out. So if you get to 1, you'll just stay there. There's nowhere else for the probability to go. Same with 4, 5 as a group. There's no way that they leak probability out. In contrast, even though probability can kind of loop between 2 and 3, it can also leak out to 1 or leak out to 4, and then it doesn't come back, right? So in this case, all I'm doing is showing that state 2 is transient and therefore class 2 is transient. I could have also shown state 3 is transient and therefore class 2 is transient. All right, another definition, so we have a lot of definitions we'll need, is the period of a state. That's the greatest common divisor of the lengths of all cycles that start at J and come back to itself. Okay, all states in a communicating class have to have the same period. All right, and we will say that a state is aperiodic if it has period 1. Okay, and if there are no cycles from a state back to itself, that's basically some form of transience. We'll just set the period to be 1 by default, okay, just so you have something to write down. And as a shortcut, if you look at a communicating class and you find a cycle of length 1, then the class is aperiodic, okay? A Markov chain is called aperiodic if all states in the Markov chain are aperiodic. Okay? Easier to see through an example. So we're going to do this 10-state example. So we're going to have a lot of different things to look at, and we'll be able to find some interesting behavior. Okay, so I'll just draw these arcs first, and then we'll get to setting up our communicating classes and then determining their periods. Okay? Right. So we have these 10 groups. And, you'll notice that in all these examples that I'm doing, we always have the classes kind of in order, like 1, 2, 3, and so 4, 5, 6, and so on. But it doesn't have to be like that. I'm just doing that because it's easier for me to draw. So communicating class 1 is 1, 2, and 3. Class 2 is 4. Class 3 is 5 and 6. And then class 4 is the remaining 7, 8, and 9. And you can verify that for yourself based on the examples we did earlier. All right, let's look at the cycle lengths. All right, so let's follow along some of these cycles. So here I have this loop of length 3. That's actually the only loop in this picture. I could start at 2 and make a loop of length 3, or start at 3 and make a loop of length 3, but that's it. Once I take 3 steps, I'm always back to myself. So there's only this length 3. There are no cycles from 4 back to itself, so we just say there are no cycles. What are the possible cycle lengths in class 3? Well, I can start at 5, come back to myself. That's length 1. I know from the previous definition that I should be done. I can say it's aperiodic, but let's just look at some other ones. I can go to 5, 6, and back to 5. That's 2, 6, loop on 5, come back to 6. That's 3. And I could keep repeating this. I could actually get any length that I wanted, originating primarily at 6. All right. And then I'm going to have, finally, here, length 2, length 4, length 6. So basically I can have any number of even length paths back to myself. So the GCD here of 3 is 3, of nothing is by default 1, the GCD of 1, 2, 3 is 1, and the GCD of 2, 4, 6, and so on is going to be 2. That's the greatest common divisor, right? So basically if you end up with some prime numbers, you're going to be okay. And if you end up with a self cycle of length 1, you're going to get 1. So basically the aperiodic classes here are going to be C2 and C3, whereas classes 1 and 4 are going to be periodic with different periods. Okay, we're finally ready to state conditions under which this limit that we're interested in exists, okay? So we want this limit to exist, and it's the following. So let me just remind you, we're interested in finite state, homogeneous, discrete time Markov chains. So they need to be irreducible and aperiodic. What does that mean? It means that there's a single communicating class and its period is 1. If those two conditions are met, then the Markov chain has a unique limiting probability state vector, and that's going to be pi vector, which is this limit that we wanted. Okay? By normalization, we said before that the sum of these probabilities has to be 1, and it turns out that all of the states will have positive probability under the conditions I outlined above. All right? And any probability vector, so if you start in any probability vector, you'll always converge to this pi vector. And what that means is that pi vector is an eigenvector of p transpose and has eigenvalue 1. So once you reach pi vector and you go and try to update it, you stay on pi vector, which is why it's the steady state distribution. And finally, if I take this update rule and I combine it with the normalization property that this is equal to 1, that gives me a system of k equations that we can solve for the k variables that we're interested in. Now, what's interesting here is that this avoids the eigenvalue, eigenvector computations, which are a bit more tedious. Okay, so that's a different way I could have proceeded to work out what pi is. But since I have this additional normalization condition, that actually allows me to work around that and just solve a system of k equations directly. Okay, let's go back to our initial example where we had this two-state Markov chain, and let's see if we can work out the asymptotic values of 3/7 and 4/7 like we had before. The first question we should have is there a unique limiting state probability vector, right? So let's go through our state classification process and determine if this pi vector actually exists. And if it exists, then let's solve for it. Okay, that's how we're going to proceed. Okay, well, the first thing that we need to do is we need to verify if the chain is irreducible and aperiodic. So first, let's come up with the communicating classes. Clearly, there's just one class here, and it consists of 1 and 2. And since there's just one communicating class, we remember that the word for that was irreducible. So we're saying that, in fact, the Markov chain is irreducible, right? And that's the first condition that needs to be met. The second thing we need to do is check the period of this communicating class, and it's just going to be 1 because there's a cycle of length 1. So there's not much more we need to do. We can just observe that 1 cycles back onto itself in one loop, in one step. So that's a cycle of length 1, it's period 1. And so the Markov chain is aperiodic because every state in the Markov chain is aperiodic and has period 1. And since the chain is irreducible and aperiodic, then we can use the result that we had on the previous slide, and we can say that there's going to be a unique limiting distribution that we're going to call pi. Great. Okay, so we're going to use the two equations, p transpose times pi is equal to pi, and as well as the normalization relationship to solve for these values. Let's start with the first one. So I have p transpose here. I multiply by the vector pi1, pi2, and that needs to be in steady state, so it has to stay pi1, pi2. So this is the steady state distribution. And so from this, I can extract the two equation, a fifth pi 1 plus 3/5 pi 2 is equal to pi 1. And I can also extract 4/5 pi 1 plus 2/5 pi 2 is equal to pi 2. It doesn't matter which one of these we use. I'm just going to use the first one to say that 3/5 pi 2 has to be equal to 4/5 pi 1. And I got that just by moving the 1/5 pi 1 to the other side of the equation. All right. And so this is going to give me the relation that pi 1 is equal to 3/4 pi 2, just canceling out the 5 from both sides and dividing both sides by 4. Okay, now I'm going to carry this to the normalization equations that they probabilities have to sum to 1. So pi 1 plus pi 2 has to sum to 1. And that tells me that now I'm going to use this, and I'm going to plug in 3/4 pi 2 instead of pi 1. And you'll see why in a moment. So I have plus pi 2 is equal to 1. Now I have a single equation about pi 2, and it tells me that pi 2 is 4/7. So this is my goal. My goal is to distill down all of these variables into relationships about one another so that when I go to the normalization equation, I'm just plugging in a single variable, solving for it, and then going back and plugging into the relations to figure out the other variables. So here, I'm going to use the relationship pi 1 is equal to 3/4 pi 2 to say that pi 1 will be 3/7. And that's exactly what we had before, so that just confirms what we saw from that plot at the beginning of the video. The last thing I'll mention is that we can also handle Markov chains that have a single recurrent and aperiodic communicating class and any number of additional transient states. Again, assuming the Markov chain is finite. So there's still going to be a unique limit, pi. And to solve for it, all we need to do is realize that the transient states are not going to have any probability left in the end. So we set their pi j equal to 0. And then I'm just going to solve for the remaining states in the recurrent class as we were doing before. We'll just do this through an example. Okay, so here's an example with 4 states. And here we're going to write out the probabilities over these arcs. Okay, and so I'm going to have a third to stay on 1, 2/3 to go to 2 from 1, a half to go from 2 to 1, half to go from 2 to 4, 3 you always exit, and 4 always goes back to 2. So the communicating classes are going to consist of 1, 2, and 4. That's one class. This is a recurrent class, and it's aperiodic. It's recurrent because none of these states leak probability into another state that then goes away. Okay, and it's aperiodic because there's a cycle of length 1, so I can easily say that the period will be 1. The other class only consists of state 3. This is a transient class because 3 does leak away probability. It's also aperiodic by default. So with that in mind, we can use these conditions above to say there's going to be a unique limit pi. And to solve for this pi, we're going to follow the steps outlined above. The first thing I'm going to do is set the transient states to have limiting probability 0. Okay, so what that means in this case is I'm just going to set pi 3 to be equal to 0. Now I'm going to solve for the pi j in C1, the recurrent class, using the method we had before. So first I have p transpose times pi is equal to pi. So I'm going to write out the p transpose here. So I'm writing out all of these probabilities, just transcribing them from the Markov chain. You can pause and verify that this is correct. And in the state vector, I'm not going to write pi 3. I'm going to write 0 in its place because I've already found it. And I have to solve for pi 1, pi 2, pi 4 from this equation. So this is going to give me a system of equations here. I'm going to write out the equations that I get. I'm going to get a third pi 1 plus a half pi 2 is equal to pi 1. 2/3 pi 1 plus pi 4 is equal to pi 2. And then pi 2 is equal to pi 4. I'm going to use this first equation to show that 3/4 pi 2 is equal to pi 1. And then I'm going to proceed with normalization. So normalization tells me that pi 1 plus pi 2 plus pi 4, again, we can ignore pi 3 because we know it's 0. This has to be equal to 1. Now I'm going to substitute pi 1 and pi 4 using these relations. So I have 3/4 pi 2 from this orange box, then I have pi 2, and now I have a half pi 2 from this purple box. Okay, all of that has to be equal to 1. That tells me that pi 2 times 9/4 has to be equal to 1, so pi 2 has to be 4/9. And now I can just go back and solve for the other two variables. Pi 4 is a half times 4/9, so it's 2/9, and pi 1 is 3/9 because it's 3/4 times 4/9. And that's it.